Hello, I'm Rahul Baghel, Assistant Professor, Chhattisgarh Swami Vivekananda Technical University, Bhilai. Welcome you all to the course on Industrial Automation and Drive. Today, we begin with our 17th lecture on PLC Counter Programming Part 1. In the previous lectures, we covered PLC timers, T-on timer, T-off timers and retentive on delay timers and their examples. So let's start the counter in industrial automations. Counter in automation systems has a similar function to mechanical counters, tracking the number of events or items that pass through a certain point in a process. Mechanical counters, shown in figure, work by moving an actuating lever which adds one count each time it's triggered. The counter automatically resets with push button. Electronic counters, unlike mechanical counters, electronic counters as shown in figure can perform various operations: count up, add to the total count, count down, subtract from the total count, and combinations. Up down counting combines both function. Up counters are the most commonly used in industrial applications. Down counter and combination counters are also significant use depending on their applications. Counter instructions in PLCs. Every PLC manufacturer include counter instruction within their programming environment. A common application in tracking the number of items, moving parts, sensors, as you can see in the figure. Counter functions similarly to timer, but they do not rely on the internal clock. Instead, they depends on external or program based signal to count. Counter representation in ladder logic programming. There are two types of representation for the counters in the PLC programming. First one is called coil format and the second one is called block format. In a coil format, a simple representation where each count is triggered by false to true transition in the run conditions. As you can see in the figure, typically up counters are shown in the figure. You can see the PR is represented the preset value and AC represent the accumulated counted value, and it is connected as an output in the ladder programming, right? Next one is block format, a more detailed representation that display the counter type, preset value and the accumulated value are found in block format programming, as you see in the diagram also, right? So let's start the detail about the coil formatted up counters. When the condition in the run changes from the false to true, the up counters increment the count by 1. Once the accumulated count equals to the preset value, counter output is energized, set to 1. Key parts of instruction includes in the coil format up counters are counter type, counter address, counter preset value and accumulated counts. And counter types specify whether it's an up or down counters. Counter address identifies the counter within the PLC program. Counter preset value, the target count to trigger the output, and the accumulated count, the current count values. Resetting counters. The counter reset instruction is essential to bring the count back to 0 or a preset value. Some PLC systems include the reset function within the counter instructions, while other use a separate instruction for resetting. The figure shows an example where a reset instruction CTR is used alongside the up counter. The reset instruction activates when its run condition is true. Next, block formatted counters. In a block format, the instruction indicates the counter types, either up counter or down counter, along with the preset and accumulated values. These counter have two input conditions. First one is count and second one is reset. Counts triggers the counter to increment or decrement. Resets the counter to its initial states. Counter operate on a leading edge of the input signal, meaning they count when the signal transition from off to on. Most PLC counters are retentive, meaning the accumulated count is preserved even after a power shutdown. Upon power restoration, the count resumes from where it is left off unless the reset condition is active. Next is counting process in PLCs. The counting process in programmable logic controller involves tracking the number of occurrence of specific events such as object passing a sensor or machine completing a cycle. As you see in the diagram also, there are two types of conditions shows the up counter condition and the down counter conditions. In these case, we have lots of process, so let's start one by one. So first process is triggering the count. In this case, first one is input signal. The counting process begin with the input signal, often from external sensor, switches or other devices. These inputs detects specific events like a part moving from a sensor. Second one is leading edge detection. PLC counters operate on the leading edge of the input signal. This means the counter increment or decrement when the signal transition from off to on state or 0 to 1 state. Next is up counters, incrementing the count. An up counter increases its accumulated value by 1 each time the input signal makes the transition from false to true. For example, if a sensor detects a part moving on a conveyor belt, the up counter incremented by 1. Next is preset value. The up counter continues to increment until it reaches a predefined number that known as preset value. Once the accumulated count matches the preset value, an output is generated, such as activating an alarm or stopping a machine. Next is down counter, decrementing the count. A down counter works in an opposite way. It starts from the preset value and decreases by 1 each time the input signal transition from off to on. For instance, if you have counting down from 10, each event should decrease by 1. Reaching 0, down counter continues decrementing until it reaches 0. When this happens, this counter triggers an output similar to the up counter, signaling that the count has completed. Next is combination up and down counters. The bidirectional counting. Some application requires both up and down counting, where the count can increase or decrease based on different input signals. For example, in warehouse, an up counter might track item being added to the inventory, while the down counter tracks the item being removed. Preset value check. In a combination counter, the process continues until the accumulated value either matches the preset value or reaches 0 depending on the applications. Next, we can see the programming in the Allen Bradley SLC 500 counter file. The file 5 is shown in the figure, as you can see in the diagram also. The counter address is represented by C5:0 or C5:1, 2, 3 up to 256. Right? Each counter is composed of a 3 16-bit word collectively called as a counter element. These 3 data words are control words, preset words and accumulated word. Each of the 3 data words share the same base address, which is the address of the counter itself. There can be up to 256 counter element, as I already mentioned. Address for the counter file 5 and counter element is 3. If I write C5:3, right, as figure is also shown, right, in the similar way, C5:3/DN is the address for the done bit of the counter. C5:3/CU is the address of the count up enable bit of the counter. C5:3/CD is the address for the down count down enable bit of the counter. Similarly, C5:3/OV is the address of the overflow bit of the counter, and C5:3/UN is the address for the underflow bit of the counter. C5:3/UA is the address of the update accumulator bit of the counter. This instruction is only used with the high speed counter, that is HSC instructions. Figure shows the counter table for the Allen Bradley SLC 500 controller. The control word use status control bit consisting of the following: the count up enable bit, that is CU bit. The count up enable bit is used with count up counter and the true whenever the count up counter instruction is true. If the count up counter instruction is false, the CU bit is false. Similarly, count down enable bit. The count down enable bit is used with the countdown counter and is true whenever the countdown counter instruction is true. If the countdown counter instruction is false, the CD bit false. CD represents the countdown enable bit. Next is the done bit, that is DN bit. The done bit is true whenever the accumulated value is equals to or the greater than the preset value of the counter for either the count up or the count down counters. Next is OV bit, that is overflow bit. The overflow bit is true whenever the counter counts past its maximum value, which is 32,767. On the next count, the counter will wrap around the minus of 32,768 and will continue counting from there towards 0 on successive false to true transition of the count up counter. Next is underflow bit, that is UN bit. The underflow bit will go true when the counter counts below minus 32,768. The counter will wrap around to plus 32,767 and continue counting downwards 0 on successive false to true rung transition of the countdown counter update. Next is accumulator bit, that is UA bit. Update accumulator bit is used only in conjunction with the external HSC counters, that is high speed counters. Next is the preset value, that is PRE. The preset value word specify the value that the counter must count to before it changes the states of the done bit. The preset value is the set point of the counter and ranges from minus 32,768 to plus 32,767. The number is stored in binary form with any negative number being stored in 2's complement binary. Next is accumulated value, that is ACC. Word is the current count based on the number of time and the run goes from false to true. The accumulated value either incremented with a false to true transition of the count up counter instruction or decrement with the false to true transition of the countdown counter instructions. It has the same range as the preset, that is minus 32,768 to plus 32,767. The accumulated value will continue to count past the preset value instead of stopping at the preset like a timer does. Let's take an actual program view of counter operations. Suppose in the first example we have the operation of a program follows the following steps. Like in the first step, operating push button PB provides the off to on transition pulse that are continued by the counters. The preset value of the counter is set for 7. Each false to true transition of rung 1 increases the counter's accumulated value by 1. In the next state, the output O colon 2/1 is energized as long as the accumulated value is less than 7. After 7 pulses or counts, when the preset counts value equals to the accumulated counter value, the output DN is energized. As a result, rung 2 become true and energized output O colon 2/0 to switch the red pilot light on. Let's take an actual program view of a counter operations. As you see in the diagram, my up counter is connected with the I colon 0/0 switch, and the output of the counter, that is done bit, that is C5 colon 0, is connected to the red button as the output. The address of the output of the red button is O colon 2/0. Similar way, my green button is connected to the address of O colon 2/1, right? As you can see in the ladder programming. So let's take the how it works step by steps. So in the first step, operating push button PB1 provides the off to on transition pulse that are counted by the counter. The preset value of the counter is set to 7. Each false to true transition of rung 1 increases the counter accumulated value by 1. Output O colon 2/1 is energized as long as the accumulated value is less than 7. After 7 pulses or counts, when the preset counter value equals to the accumulated counter value, the output DN is energized. As a result, rung 2 become true and energized output O colon 2/0 to switch the red pilot light on. At the same time, rung 3 become false and de-energized output O colon 2/1 to switch the green pilot light off. The counter is reset by closing push button PB2, which makes the rung 4 true and reset the accumulated count to 0. Counting can resume when rung 4 goes false again. You can also see in the timing diagram, right, for this procedure. To understand this counter operation, let's take another example. In this example, PLC counter program used to stop a motor from running after 10 operations and on red pilot light, right? So let's take a program. As you can see in the ladder programming, right? In the ladder programming, we have two input switches. First one is a start and second one is a stop. The address of a start button is I colon 0/0 and address of a stop button is I colon 0/1. And these two switches, in the first rung, these two switches are connected with the binary output, that is B3 colon 0/0. And this binary output is provided as an input switch for the counter CTU, that is C5 colon 0. You can see in the second rung, and the counter value is, the counter preset value is 10, right? In the fourth rung, the counter done bit is connected to the red light, and in the third rung, the same binary output address is provided to the switch, and the motor is connected as an output in the rung 3, and the address of the output motor is O colon 0/1, and the address of the red light, output red light, is O colon 0/0. So let's take step by step or case by case. So let's take in the first case, when start button is 0 or start is 0 or off condition, means it remains it there, it remains it in initial state, that is normally open stage. That's why my binary output B3 colon 0/0 is off condition. That's why my counter is also in off states. That's why the output connected to the counter done bit is also 0, that is red pilot light is also 0. In the same time, motor is also connected to the binary bit is That's why so motor is also 0. So in the initial case, all the outputs are in the 0 state, right? Next case, when I press the input switch or start button, I colon 0 slash 0. When I press the start button, as you can see in the diagram, the binary output goes high, and when the binary output goes high, my counter gets the supply. That's why the counter enable bit goes high and it incremented by 1 because it changes state from off to on, right? That's why the counter accumulator value changes from 0 to 1. At the same time, you can see in the third rung, my binary output is connected to the motor. That's why motor is also on, right? But in the same time, you can see in the fourth rung, my counter done bit is 0. That's why my red light is in off state. In the next case, when the red light is pressed, suppose when the red light is pressed means when I restart the process or when I stop the process, we can press the red light. My B3 colon 0 goes 0 or of an off state, and the same time motor is also goes 0, right? When this on and off process repeat 9 times, my accumulator increases by the 9, right? In the next case, when this on and off process repeated the 10th time, the accumulator value is equals to the preset value. That's why C5 colon 0 slash done bit is equals to 1 and the motor goes off, right? And the red light goes on because the red light connected to the counter done bit. So you can see that when accumulator is equals to the preset value, my counter done bit goes high and the output connected to the done bit is also goes high, that is red light goes high, and in the same time you can see that my done bit interconnection provided in the first rung, that is C5 colon 0 slash done bit provided in the first rung, is also activated. That's why my binary output goes 0, and when the binary output goes 0, my motor will be off after 10th time of off and on programming, right? I think you clear this program. I'm again repeating this process to proper understanding of your counter programming, right? See, we have one problem or one problem statement, this like we have our motor to stop after the 10th operations. If our motor is working and the 10 times it's on and off, then our motor will be stopped, right? So this is basic programming objective. So in this case, we took two outputs, one is motor and one is the red palette light, right? And two inputs for start and the stop button. Start button is represented by I colon 0 slash 0 and a stop button is represented by I colon 0 slash 1. See, when I press the start button in the first rung, you can see when I press the start button, my binary output goes high, that is B3 colon 0 slash 0 is high. And you can see my binary output B3 colon 0 slash 0 is provided to the input to the my counter, that is C5 colon 0, and the counter preset value is set by 10 because the objective of my program is we have to stop my motor after 10th operations, right? That's why the preset value is set by 10. So when I press the start button, my binary output goes high, and when the binary output goes high, my counter gets supply, right? My counter gets supply by 1. So my counter accumulator increases by 1. Getting my point? And the same time you can see in the third rung, the binary output is connected to the motor. That's why motor is also goes on, right? And the same time you can see the counter done bit is connected to the red pilot light, because in this case done bit is not activated, that's why red light is in off state. So what happened, when I press the start button, my motor is start and my counter increases count 1, right? Next, what happened when I stop my motor? So I'll press the stop button. When I press the stop button, my binary output will be off, and when the binary output will be off, my motor will be off. In the next condition, again when I start the start button, again I'll start with our process through the start button. That means my binary output again gets the output and it will become start, and the same time my timer also my counter also gets the input. That's why it's again incremented by the 1, right? And the same time motor is also getting power, so motor is also start. Means my motor on and off process continues to the 10th time, right? And after the 10th time, when my counter count value, means counter accumulated value is equals to the preset value, then my done bit will be high, right? If my done bit will be high, then the output connected to the done bit goes low, right? Why low? As you can see in the first rung, because done bit represented as a normally closed switch, when the done bit goes high, that normally closed switch converted to the normally open switch, that's why the binary output goes low. But in the fourth rung, you can see when the done bit is high, the output connected to the done bit goes high, that is red light goes high, right? So this is my counter programming. Counter programming is just similar to the timer programming, but the basic difference is the timer and the counter programming. In the timer programming, we provide continuous supply to our timer, but in the counter programming, it doesn't require to continuous supply. When it gets supply, it incremented by 1, and when again going to off state and then again getting supply, then it incremented by 1. So it's continuously getting signals and it's incremented, right? But in case of timer getting continuous supply, and for that time it start counting, right? In the same time, our timer is also two type, up counter and down counter mainly. Similarly, our counter is also two types, up counter and down counters, T on and T off. Similarly, CTU and CTD, on timer, off timer, up counter and down counters, right? So process is similar. The only thing is when the done bit and enable bit is high, that is most important, right? So that's all for the today's programming, today's lecture. In this lecture, we cover the types of PLC counters, PLC counter instructions, up counter operations, and some examples related to the PLC counters. In the next session, we will explore more on the counter programming with the countdown process, and also explore with the one-shot rise instruction, that is OSR, one-shot instruction, and one-shot rise and one-shot down instructions. In this lecture, we cover the types of PLC counter instructions, and up counter operations, and some examples related to the up counter. In the next session, we will explore more on the PLC counter programming related to the down counters, and also explore the one-shot bit program and the one-shot rise and one-shot fall program how it works and how it related to the counter programming and how it helps the ladder programming. So thank you so much and happy learning.